It's a type of video game where you're not supposed to beat it the first try. You're supposed to die a bunch of times, and every time you die, you get better. And hopefully by the end, you can beat it. That's what today's lecture is going to be. You're not going to understand it at first, but that's okay, because you're not being tested on it. Today is a very special lecture because I guarantee you, no matter which discipline you pick, because I know that right now you're just civil, you'll use the finite element method. Geotechnical, you use it all the time. Structural, of course. Transportation, why not? Even mechanical engineers use it all the time. That's why I love it so much. I became, or I'm going to use this in quotation marks, an expert in this particular topic because now I'm not limited to structural. I can go simulate a chemical plant. I can go simulate a car engine. It's all the same. That's why I love the finite element method. Before we get into that, though, just some updates about the exam. Is everybody comfortable with the exam? They know the exam time. It doesn't conflict with anything. Perfect. So one remark is the review sessions. I'm thinking I'm just going to do them independently, posting them to YouTube, because then I can get them out sooner. And if you have any questions, you can come see me. So I'm available every day from now until the final. So if you have any questions, let me know. I'm going to put timestamps in the YouTube videos. So let's say that you're just having a problem with question 18. You can just click and it'll go right to question 18. That's my hope anyway. It'll make studying easier for you. The reason why I decided this was because I was trying to figure out when to do them. If we're doing 50 questions in 2014 and 50 questions in 2015, well, chances are we need 4 review sessions. Are you guys going to be available 4 nights between now and next Thursday? No, of course not. I was thinking, well, I can do it over the weekend, but no one wants to do that over a weekend. And I thought, okay, we'll do it next week. Well, I know half you have 372 next week, so it's not going to work out pretty nicely. So yeah, I'm going to do them independently. If you have any questions, though, of course, let me know. I'm going to hopefully have them up before this weekend, so you have plenty of time. I'll have the videos for both 2014 and 2015, and I will just post my solution PDF of both of them too. So you have 100 questions total. Does that sound good to everybody? Perfect. Any questions at all concerning the final assignments or anything like that before we begin? No? Wonderful. So then I have one more question for you, and this is going to sound pretty silly, but do you guys have class tomorrow? One class? I don't know if today's the official end of the semester or tomorrow is, before the National Day of Reconciliation makeup lecture. Basically what I'm wondering is, do you guys want to, we have one more lecture, which is going to be the actual software, which is going to be online. Do you want to have that tomorrow or Thursday? Who wants tomorrow? Okay, who wants Thursday? Okay, perfect, so it'll be tomorrow. So tomorrow, online students do, because you're usually the ones messaging me the most, we'll go into Abacus software. Now, Abacus software isn't the best for you guys for finite elements. Abacus is a very generalized software. Inside of it, I can do anything I want. I can simulate anything. It's extremely powerful, but as you're going to see, there's going to be kind of a trade-off. It's powerful in the sense that I can simulate everything, but it gets very complex because, again, I can simulate everything. A lot of the programs you will use as, let's say, structural engineers won't be as powerful. It can only simulate very specific things, but then it's more user-friendly. So that's kind of the trade-off. Abacus is the worst because it's not user-friendly at all, but you can simulate everything. In structural design, unless there's very specific circumstances, do you think that we actually analyze an entire building in one simulation? What do you think? Who thinks yes, of course? Who thinks no? The answer is no. What we typically do is we look at areas of concern, and let's say I'm concerned about this column falling over. Well, that would be something I simulate. All I have to do is define the boundary conditions at the top and the bottom, then I can simulate the actual column. So actual simulation becomes quite complex, as you're going to see, especially if you take structural. Now today I'm going to talk about kind of the basics of the finite element method by talking about perhaps the most general one, which is solid elements. So every time you Google finite element method and you get that nice rainbow plot, those are typically from these solid elements. Now the nice thing is Civi 665, the other course I teach, it's actually called the finite element method. We're going to start on lecture 5, but lecture 1, 2, and 3 is actually something you guys already know. Lecture 1 was a linear algebra review. Does that sound familiar to you? Lecture 2 was solid mechanics, stresses and strains. Did we cover that? And lecture 3 was approximation methods, virtual work, Rayleigh-Ritz. Did we cover that? Yes. Lecture 4 was bar elements, and those aren't something that you typically see too often, so I'm going to leave it out. But lecture 5 is solid elements. As we're going to see, a lot of the stuff that we're going to talk about is stuff we've already covered. We're just taking it from a very general sense, and we're making it to a very simplistic sense. What do I mean by that? Well, when we solved for displacements, were you given the displacement in terms of a constant, or was it usually a function? Think of the Rayleigh-Ritz method. When we solve for displacements, did I get my displacement to be 10 millimeters, or did I get it to be something x1 plus x1 squared, or something like that? Was it a function? It was a function, meaning that I found the displacement, or the approximate displacement, at every point along my beam, every single point. All I had to do is substitute whatever value of x1 that I wanted, and I get my displacement. The finite element method doesn't quite do that approach. It does something a little bit different. We are going to look at displacements at select points, as we're going to see. So we're going to jump in. I don't think we'll finish this lecture. As you'll see, graduate lectures are a little bit longer than undergraduate lectures, but we'll see how far we can go and how quickly I can lose you guys. So the first one is general solid elements, and this is a general case. So in the last lecture, which you guys didn't see, we basically used a method called the Galerkin method to apply, or basically take our two differential equations, one for bars, one for beams, and we can figure out their element formulations. We're not going to discuss that in this lecture. What we're going to talk about today is 2D solid elements. Now this is all going to be based on continuum equilibrium. You remember those equilibrium equations that we had? We are going to do the same thing here. Now the key thing is this. When we did an approximation method, did we discuss applying those equilibrium equations to a very specific approximation method? Do you guys remember? Which one? Which is the one you all hate from 372? Virtual work. That's going to be the entire key to these questions. We said we can figure out an approximate solution if we know stresses and strains, right? That's all we needed to know for internal virtual work. Well, as we're going to see, that's going to be the whole basis here, is how can we find the stresses and strains of these elements? So let's say that we had this scenario here. Could I solve this scenario using an Euler-Bernoulli beam formulation? What do you think? No. What do you think if I used a bar element? Good results? No. As we can see, the cross-section thickness decreases. We have a load kind of applied diagonally at a point. We have a lateral load. It's going to be a mess. So what the finite element method does, it says, okay, well, instead of solving for the displacement at every single point, we are going to concern ourselves with the displacement at select points. So this is going to be the terminology you see. All of these green points, these are called nodes. It's going to be very specific when we actually talk about it in software. And each node forms an element. So this triangle right here would be called an element. And as we can see, we have 1, 2, 3, 4 elements. Now, what the finite element method does is it basically calculates the displacement at the nodes. That's it. So here, 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 and here, and here. So we have 6 locations of interest. Because if we know the displacement, let's say we know the displacement of these 3 nodes. So for this triangle here, Can I approximate the displacement inside of the element if I know the displacement around the boundaries? What do you think? Is that too much? No, of course I can. So that's the entire goal. We're taking a complex problem and we're splitting it into smaller, discrete problems. So what the finite element method does, in essence, is it takes a big problem, splits it into these smaller elements, solves each element individually, and then brings it back into the bigger problem. Now we're going to look at the actual formulations. So if we look at this element, it has what we call degrees of freedom, basically meaning that each one of these nodes can deform in a specific way. For instance, if we were to have a general coordinate system, u and v, well, we know that our displacement is going to be u, which is basically the horizontal displacement, and v, which is displacement vertically. But again, this would be for a general case. What we want is we want to convert it to just the displacements at these nodes. So what we do is we have an approximation function. Starting to sound familiar to you guys? Approximation function. And this approximation function is actually going to depend on what type of element we use. So right here, I'm using a triangular element, but do you think that we have rectangular elements? Yes. And inside of these elements, we have different orders. And basically, what element you pick is actually only going to change our approximation function. That's it. All of the different elements, the only thing that they do is change our approximation function. In this slide, though, we're not going to look at a specific element. We are just going to keep it extremely general. So the degrees of freedom. Again, in this finite element method, we're expressing the displacement in terms of nodal displacements. I don't want the displacement at every point. I only want the displacement at my nodes. So instead of this scenario here, what we're actually going to look at is this scenario, where this node is going to displace u1 and v1. This node is going to displace u2, v2. And this node is going to displace u3, v3. So we're only concerned with, again, these three displacements. From here, we can actually express our displacement function as a function of these nodal displacements at the end. So you notice how I have u1, u2. In this case, it would stop at u3, but in the general sense, it can go on forever. Now, what's important is we have something called n. n1, n2, all the way up here. These are shape functions. And it's basically this. The best way I can describe it would actually be to show you a picture. If I were to have a bar element, so let's just say I have a bar element. I have my two nodes at the end. And let's say that I know that after some load, this node displaces upwards here, and this node displaces downwards here. Let's say that I also know that it has a linear approximation. If I know those 2 points, can I figure out that equation describing that displacement? Yes. This equation would actually be our shape functions. So our shape functions take our displacements at the boundaries, or our nodes, and it's used to approximate the displacement throughout the entire element. And we'll talk more about them for specific elements. That's all I did. Again, instead of a general sense, I only have displacements at 3 points, and I can express our total displacement as a function of those 3 displacements. Now from here, what I'm going to do is I'm going to take this displacement function and I'm going to factor out n1, n2, all the way to nn. So as we can see, we have a matrix, n0, n2, 0, all the way to nn, and then we have our nodal displacements right here. So for this particular vector, or sorry, this particular element, what would the size of this vector be for this particular element? If these are my nodal displacements, u1, v1, u2, v2, how big would this be for this particular element? 6. As we can see, 1, 2, 3, 4, 5, 6. Now here's going to be the fun part. That size here, well, that's actually going to be the size of a matrix used to describe this element. So one of these elements, as we're going to see, is going to be 6 by 6. That's one element. How many elements do you usually see when you run a simulation? Thousands? Probably. And every element is a 6 by 6 matrix. So you can see how complex this is going to get once we start having all of the elements. So now this is actually very nice because what we did is we factored it into two different things. The nodal displacements, which are constants. So that's going to be the key here. Is this, or do you expect that this point is going to have a displacement as a function? Think about when you solved the Rayleigh-Ritz method. You found the beam in terms of x1. If we know the specific point that we want, do we technically know x1? Yes. So all of these right here, these nodal displacements are going to be constant. Now, think back to what I said about these shape functions. These right here are used to take our nodal displacements and approximate the displacement at every point inside of our element. Are these going to be constant? What do you think? Are these shape functions going to be constant? No, they're going to be a function of x1 and x2, because again, they're taking these displacements and they're approximating everything inside of the elements. So, oh, and then we can simplify it into n times e. Again, these will be a function of x1 and x2. These will be constant, and this is going to be important later on. So now what I want you guys to know is just that we now have the displacement of this element as a matrix n times a vector u. That's it. Because if we know the displacement, can we find strain? Yes, we can find strain. So that's what we are going to do next. We know that since we have a displacement, we can find the strain components. All we had to do was take the displacement gradients and then go 1/2 nabla u plus the transpose nabla u. So again, we're in 2D, so we're going to have 3 strain components. And we know from basically the small strain tensor that these are going to be the components. Now, if I know what u and v are, can I take their derivatives? What do you think? If I know u and v, can I take their derivatives? Yes. This first row here in red, this is u, and the second row here in purple, that's v. So what I can do is I can find the strain tensor as this nice thing right here. So all I did to find these components, for instance, if I'm looking at this first row right here, all I'm doing is I'm going down and I'm simply taking the derivative with respect to x1. So n1, I just took the derivative with respect to x1. 0, well, I'll take the derivative at 0, n2, etc. Am I scaring you yet? Is the math starting to look pretty gross? Yes. But here's the nice thing. Do you think we would ever do the finite element method by hand? No. We use a computer. Now, take a step back from the math. Does this look nice for a computer? It looks very nice for a computer. And the reason why is this. n1, 0, n2, 0, n3, 0, n4 is repetitive. So all you need to do is throw it into a for loop. So what we end up getting is that this strain vector is equal to what we call a B matrix, which is the derivatives of all our shape functions, times this nodal displacement vector. Again, this nodal displacement vector is constant. It's this B matrix that is actually going to be a function of x1 and x2. And we just call it the B matrix. It's pretty simple. So that's going to be strains. Now, question for you all. If I know strains, can I find stresses? Yes. So that's what we're going to be doing next. If we know the strains, we can calculate the stresses. So if I wanted sigma 1, 1, 2, 2, and 1, 2, well, we know it's just going to be a constitutive law times our strain vector. Now, for two-dimensional scenarios, what are our two laws that we have? Do you remember? Plane stress and plane strain. So one of the things that you'll see in Abacus when we're defining our elements, it'll ask you, do you want plane stress or plane strain? Which is nice because you now know the difference between the two. So this is just going to be C times E. And again, all we are going to do for C is use plane stress or plane strain. So we can use plane stress or we can use plane strain. It's up to you. If I wanted to model a wall, let's say I wanted to model this entire wall. And let's say that we had a load acting kind of at the top here. Would I use plane stress or plane strain? The wall is very thin in that outwards direction compared to its length. What would you use? Stress. Because is there anything restricting this wall from expanding into that plane? No, there's no boundary conditions. So that'd be plane stress. E is the Young's modulus, mu is the Poisson's ratio, we're good to go. Because we can now express this, since we know what the strain is, as C times B times our nodal displacements. Now we are going to take both of those, because we know stresses and strains, and apply it to the principle of virtual work. So you guys remember that nice big equation? Internal virtual work is equal to external virtual work. And if we're looking at the continuum case, we derived the following equation. You remember this? Do we know what our strains are? Yes. Do we know what our stresses are? Yes. We can figure out everything we need in here. So if we're going to look here, we have strains, and on this side we have stresses, which again we know. So our strains are going to be B times our matrix here, our nodal displacements, and then our stresses are going to be C times B times our nodal displacements. And this is why I said it's important to note that these two nodal displacements are constant. Because if they're constant, can I take them out of the integral? Yes, I can take them outside of this integral. And another thing to note is since we have virtual strains, this is technically a virtual displacement. Now what I'm going to do is going to be a little bit funny, is I'm going to rearrange these two terms. If I want to move B to the other side, I need to actually take the transpose of it. So I just swap these two around, because now with my nodal displacements at the end, I can factor them out because they're going to be constant. So I get this expression right here. Now this is actually pretty nice because it goes back to what I told you before. When we're dealing with structural analysis in a software case, we always have stiffness times displacement is equal to force. If we look here, we have a matrix times displacement, and it's equal to something which is probably going to be force. So this is what we're going to do for the internal virtual work. On the other side, for the external virtual work, we are going to tackle this problem right here. Traction vectors and body forces, those are externally applied, so we don't have to worry about them. It's these displacements. In its current state, these are the displacements throughout the entire element. But we said that we can take those displacements and express them as n times our nodal displacements. So that's all I'm going to do here. We are going to have n times our nodal displacements, but then I flip the nodal displacements over to the other side. From here, I can actually factor out each and every one of them to get the following. Now, if they're constant and they appear in every single term, can I just get rid of them? Yes, of course. So we're going to get rid of those, and we're left with the following equation. Now, in the most general sense, this is the equation for each element in your system, every single element. So every element that you define is going to have to go through this process. I'm hoping now when you look at this, you understand why these programs take a lot of time to run. However, what we're going to see is we can play a lot of tricks to make this simplified. In Abacus, everything comes from this, so nothing's too crazy, but I'm going to let you on a little secret. We don't do any integration in Abacus. What do you think? Is that allowed? It must be, because I said it's true. What you will find is that a lot of work has went into simplifying these as much as possible. But we're going to go on a little bit further just to see what happens. Now this is what I wanted to show you, this right here. We basically have this term, an integral, which is going to be the stiffness of our element, multiplied by a displacement, is equal to force. This part right here is something we can actually solve right off the bat. So we can figure out the stiffness. FE, our loads, these are something that are applied externally, so we will know these. If I know K and I know F, can I find my nodal displacements? Yes. The only problem is this is a matrix and these are vectors. So if I want to move k to the other side, solve for these displacements, I have to inverse it. I have to inverse a matrix. And we said for those triangular elements, k is 6 by 6. If I want a quadratic triangular element, it's 12 by 12. If I want a 3D cube element, it's 30 by 30, just for one element. So as you're going to see, this is actually what takes the most time, is taking this and flipping it over to the other side in a linear analysis. That's the worst part. We're going to talk about the nodal forces really quick. Got that. Stiffness matrix, nodal forces vector. This is just a summary. I think I talked about these a little bit more in the next slide. So what I want you guys to take is, this is the general sense. So for any element, you can use these equations. But as we're going to see, we're not going to talk about any element. We're going to talk about very specific elements. So both are needed to determine nodal displacements, which you guys probably know. We didn't define the shape functions. I told you what the shape functions are in essence, but we never talked about what exactly they are. And these will actually depend on the element type and geometric order, which you guys don't know. We're going to discuss that really quick. I'm just going to fly through 3D elements because we're not going to focus on them too much. It's the exact same process as before. Could you imagine doing that by hand? Wouldn't be fun. That's what I made the graduate students do. They didn't like me. We can do the exact same process. Virtual work, same thing. All right. So this is kind of important at the end here, and that is this idea here. Whenever you run finite element results, chances are it's not going to be that nice, pretty, colorful picture that you all get, because all these elements are actually what we call C0 continuous, meaning that the displacement of each node has to have continuity. So as we can see here, there is continuity on this displacement. When we start taking derivatives, of course, which we need for stresses and strains, there's going to be no continuity. So this would be one element, this would be a second element, and as we can see, we have discontinuities. If we were to make the stresses also continuous, the same thing with displacements, things get really hard. For instance, if I have an element in the center, this element is going to be impacted by this element and this element, the two that touch it, and that's it. If I want to ensure continuity between stresses, well, then an element all the way over here is influencing this element, which becomes really complex mathematically. So we typically just leave it as C0 continuous. The only reason why I'm mentioning this is because in Abacus, when you get your results, it'll say that the stresses are averaged, meaning that what Abacus will display is this stress and this stress average. So it displays something like this. So your pictures in Abacus will actually look nice and continuous, but it's important to note that in actuality, it's not. I'm just trying to highlight the key features you'll notice in Abacus. We're going to go into triangular elements. So again, what we just described, that was the basic formula that can be applied to anything. But now let's see if I want triangular elements. I know I'm putting you right to sleep, but I'm trying to cram so much into one little lecture. So we had this formula from before. For our stiffness, we had this for our nodal forces. Basically, we said that this B matrix, as well as N, depends on those shape functions. So how do we find the shape functions? Well, it's actually pretty simple. For a linear triangular element, we have 3 nodes. One at the top, bottom, and then the other corner. 3 nodes. For a quadratic triangular element, we have 6 nodes. Now this is actually going to be important. Remember, nodes tell us the displacement, or that's what we're solving for, the displacement at these nodes. As we are going to see, there's going to be a lot of limitations. And this is one of those things that I always laugh at in the capstone exam, because people try to use the finite element method, but there's a lot of limitations you don't know. For instance, this right here is going to be the one we examine first, and you'll learn that this element is garbage. It has very nice properties for some applications, but for a general application, it's actually a pretty garbage element. This one's better, of course. If you have more nodes, the better the element's going to be. But will this one take longer to compute? Yes. So that's the trade-off here. And we're going to look at those limitations. So let's look at the linear element first, which we also call the constant strain triangle. We have we have 3 nodes, 1, 2, and 3. And then we are going to define the height and the base as simply 1. From here, we are going to have the following approximation function. U and V is equal to A naught plus A1 times X1 plus A2 times X2. This right here is a linear equation. So as I said, those approximation functions that we had to define in the Rayleigh-Ritz method and all that fun stuff, in the finite element method, we've actually have them all predefined. And the important thing is to see their limitations. So what we want to do is take this general displacement function of this element and express it in terms of nodal displacements as well as the shape function. So again, we wanted those shape functions. So what we do is we say, okay, we have the following nodal displacements, and each node has 2 degrees of freedom, one in the horizontal direction and one in the vertical direction, which leads me to my other key abacus points. If these nodes only have displacement degrees of freedom, can I define a restriction on rotation? What do you think? If I had a fixed end here, abacus is going to say, do you want to fix the rotation on these nodes? Can you fix the rotation? You can, but is it useless? Yes. So that's the very first thing, and probably the most common question I get asked by people trying the finite element method for the first time is they specify these to be completely fixed, and then abacus gives them a warning. It's not an error because abacus is so used to this, but it's a warning saying, hey, you don't need them. And this is why, because we only have displacement degrees of freedom. So what this turns out to be is U1 times N1 plus U2 times N2, U3 times N3. How do we get the shape functions? Well, it's actually pretty simple. All we do is we take our function, and I should have moved that over to the other side, and we investigate basically the case where we have a linear relationship between the nodes. So this would be my shape function N1. So it's hard to see, but N1. What we do is we take node 1, we displace it by a unit displacement, so this would be 1, and we keep the displacement here, and here the other 2 nodes is 0. If I know the displacement here is 1, and the displacement at these 2 nodes are equal to 0, can I figure out the equation of this plane? What do you think? Yes. That's all I did. I took this as here, I set these 2 as 0, good to go. What you'll find is that for the constant strain triangle, N1 is equal to 1 minus X1 minus X2. We can repeat the same process for N2, so I'm going to take, I think it's this node, apply a unit displacement upwards of 1, these 2 stay 0, N2 is actually just equal to X1. And then the same thing for N3, I find that N3 is equal to X2. Now that we know the shape functions, can we determine everything in our stiffness matrix? What do you think? No one knows. I know I've lost you guys. I'm just talking at this point. Again, you don't have to know all this because this is outside the scope. I'm just trying to show you the limitations. I don't even want you guys to understand the formulations. Again, the key things are I just want to point out specific things so that when we get to abacus, you'll say, okay, I know why not to do that, or I know I should do this. That's all I'm trying to do. So our N matrix is this, but now since we know N1, N2, and N3, we can substitute it as follows. From here, we can find the B matrix, because remember, it was just partial derivatives of our N matrix as follows, and then we get our B matrix to be this. So before, this scared a lot of students, but our B matrix actually just turns into a bunch of -1s and 1s. Now tell me this. We said that our strain vector was equal to B times our nodal displacements. Our nodal displacements, are they constant? Yes. Is this B matrix for this particular element also constant? So what are my strains going to be throughout my element for this particular element? If B is constant and my displacements are constant, constant. Is that a problem? Yes. I put this slide up, actually. Let's say that we wanted to model this beam right here, so I'll zoom in a bit. And let's say that we use triangular elements, so something like this. We just finished saying that the entire strain in one of these elements is constant, meaning that if I were to run abacus, my strain in this entire element is going to be the same value. In these types of beams, does the strain change as we go down? If I were to load this beam vertically, would the top be in tension or compression? Tension. What about the bottom? Compression. So obviously there's a change in strain. We go from tension to compression. If we were to use a constant strain triangle or a linear triangular element, can we capture that? So what would the results be? Garbage. Complete garbage. So this is why it's important to note some of these formulations. Again, I don't care if you can reproduce them or not. I'm just trying to show you the limitations. So when it comes to bending, would we ever use a constant strain triangle? Probably not. Okay, here's the thing. If I were to go up to this scenario, and I were to analyze two constant strain triangles here, what abacus will tell me is there's a constant strain, but this will be in tension. It also tell me that there's a constant strain, but this will be in compression. So can this model bending technically? Yes. But if it's assuming the same value of tension throughout this entire segment and then the same value of compression, is it going to be a good approximation? No. What happens if I add another layer? Will it become better? Yes. And how about another layer? Even better? Yes. But remember, each one of these is a 6 by 6 matrix you have to add to the system. So every time you try to make your approximation better, you are also drastically increasing the runtime, which you don't really want to do. So this would be our V matrix. Now, one of the things that we've also discussed is that we can have a quadratic element. We're not going to get into the formulations too much, but this is what I want you to know. If these were quadratic functions instead of linear, will this N matrix also be quadratic? Yes. And if this is quadratic, and I were to take derivatives, would this be constant? No. So you can have our strain matrix as basically functions, but then again, it increases your runtime, which I'm not sure you want to do. So from here, we can actually find the stiffness matrix because we know B, we know C, depending on plane stress or plane strain, and then we know B. So basically, we assume a thickness into the plate, and we integrate. Do you guys know how to integrate a matrix? It's simple. All you have to do is integrate each component. But as we can see, for that one triangle, which is the simplest element we have in our library, this is what abacus has to do every single time for every single one of these elements. B transpose, C, and D. Results in a 6 by 6 matrix. We can actually simplify the nodal forces vector because we now know what N is, and we integrate over the volume. And we can do the same thing for the traction vector, integrating over a surface. As we were seeing, there's going to be a lot of integrating. It's pretty gross. Quadratic elements, all it basically is we're taking our approximation function, and instead of assuming linear, we are now going to assume it to be quadratic. That's all we're doing. In abacus, or actually, let me ask you this. Do you think that we can have a cubic element? We looked at the linear elements, we looked at a quadratic element. Could we have a cubic element? Do you think abacus has a cubic element? No. Because if this is already quadratic, you can only imagine how much longer a cubic is going to be. We said one thing with the linear element is that yes, it's garbage, but if we add more, could we have a good approximation? Yes. So that's going to be a key thing for you as designers. Would you rather have 3 linear elements or 1 quadratic? Which one's going to be better? Who knows? There isn't a clear answer. So when you see finite elements, and when you look at any research papers, or if you look at me when I'm in the structural capstone, that'll be my first question. What kind of elements did you use? Why? How do you know that they're good elements? Always your runtime, all that fun stuff. So as we can see, it starts to get really complex. And if we have 6 nodes, and each node has 2 degrees of freedom, what is our matrix going to be? What do you think? Remember, this will result in a matrix for stiffness. For the linear element, I said it was 6 by 6. What do you think this one will be? It'll be 12 by 12. Basically, every node times its 2 degrees of freedom. So 6 nodes times 2 degrees of freedom per node, 12 by 12. It gets pretty messy. So this will be our shape functions, and we can determine those shape functions by the same process we did before. So for N1, I'm going to displace node 1 by a unit displacement, and all of these are going to have 0 displacement. In order to make this possible, these have to be quadratic functions. You know how long this took to make in PowerPoint? That wasted my whole weekend. This is N1. I didn't even bother with the other one, so we can solve for all 6 of these functions. Going to get very messy. So our N matrix is now the following: N1, 0, N2, 0, etc. Running out of colors. This is our B matrix, and since we know each one of these is a function of x1 and x2, we can actually solve for our B matrix. Let's see if I even do it. Was I brave? No, I wasn't brave. I didn't do it. All right, so quadrilateral elements. These ones are the most common. These are square elements, basically square. Whenever you see most finite element analysis, you're going to see these square elements. Again, same process as before, but now we are going to have 4 nodes. If we actually look at what we're doing between these triangular and quadrilateral elements, the only thing we're actually doing is changing our approximation. That's it. If you look at the steps, which I have all these online, so you can look at it if you want to. I don't expect that you want to, though. The only thing that changes is our approximation function. That is it. Because if we change our approximation function, we change our shape functions. Once we have the shape functions, everything else is the exact same. So just like before, we have a linear case and we have a quadratic case. So the quadratic case, as you're seeing now, is just an extra node at the midpoint of each surface. If we were to solve it, it's pretty simple. We have the following displacement function or approximation. So remember, for the linear triangle, our approximation was just this first part right here. For quadratic, we add this extra part right here. And this is actually a typo. I can't believe it. Someone said this. It should be x2, not x3. We're not in 3 dimensions. So if we know this, we can actually determine this as a function of our shape functions in the same process. And then from there, we can find our shape functions. So we'll just run through. Again, the shape functions are the same process. Apply a unit displacement at one node, it's 0 at the others. Because then after we have our shape functions, we put them into the partial derivatives, and we get the following B matrix. Now, a question for you guys. Is the B matrix constant now? No. So will this be able to predict bending? Yes, it will be able to predict bending, but as you will see for linear elements, there's actually a little bit of a problem, and we'll discuss a little bit later. So we have everything that we need. We can substitute it into our equation, and remember, this is just for one element. So we can find out what our stiffness of that element is. This would be an 8 by 8 matrix. Do the same thing over here. Again, this is just for one element. But here's one problem. One problem with the linear elements is shear locking or parasitic shear. And it's basically this right here. If we were to take a beam and bend it, we know that this is what we'd have, right? Does that make sense? This is our behavior. Is this deformation linear? Is this curve right here linear? No. But in these elements, are we assuming the relationship is linear? Yes. So if we look, we actually have this behavior right here, where these two will compress, these two will go out in tension. But do we have any strain here? Basically, no. It results in our element actually being too stiff and bending because it actually doesn't account for this behavior. So if you're doing bending, you have to have at least a couple of these elements in a row, or else you're going to get stiff results. A quadratic element, it's the exact same thing. You can see how messy this is going to get, of course. Shape functions, and it's just the same process. A lot of fun. You guys still awake? So let me ask you right now, how does the finite element method sit with you? Yeah, of course.
When you say like in force or United, what you got to do is really learn this?
You do not learn this at all. And that's why one of those things is a lot of students will ask me about doing a graduate degree. And I tell them, well, unfortunately for structural, you'll have to. Because a lot of the stuff you don't really learn. Another key one is dynamic finite element method. Everything that we're learning here, did it involve time? No. If I were to load a structure really fast, is it going to have a different behavior than if I load it very slow? Yes. So basically what we see is a lot of the stuff that we're learning, it's pretty basic. You don't learn how to model. You don't know how to do proper analysis. You don't know the proper behavior of concrete. Basically, when you come out of undergraduate, you'll learn how to design a beam. Not much else, unfortunately. But it's one of those things that graduate school's fun, as you can see. Aren't you having fun right now? No? I'm going about the same pace as I would in a graduate lecture, so you can see how fast it would be. As you can see, it's just a lot of skipping over a lot of stuff and expecting you to self-study. I've calculated the most of what I want to actually talk about. 20 notes for a quadratic brick element, a lot of fun. So let's actually just talk about the system as a whole, because that's one thing that we didn't actually discuss. So we're going to just look at, that's highlighter. I want to look at these two scenarios that I have on my screen. Put this down. Everything that we said was basically this. We talked about the general formulations of an element, but the finite element method is so much more than that. The first thing is this. For this one element, we said that it is going to be, 8 by 8, if it's linear. 8 by 8. That's the stiffness matrix for that element. When we analyze the entire structure, are we just looking at that one element? No. So what do you guys think, would be the stiffness matrix, or the size of the stiffness matrix for the entire structure? First thing you have to do is you have to look at the nodes. If it's linear, we only have nodes at the corners. So this element has 4. This element has 4. Same with this one. Same with this one. So as we can see, we have 2, 4, 6, 8, 10 nodes. And each node has 2 degrees of freedom. So how many, or what is the size of our matrix? What do you think? 20. 20 by 20 matrix for 4 elements. But you guys see the problem that the finite element method starts having. When I calculated the stiffness matrix for this first element, it included these 2 nodes. But when I calculate it for the second element, does it also include the same two nodes? So not only do you have to calculate each element, next what you would have to do is figure out how they interact with each other. In a proper finite element analysis, should this node, or sorry, this element predict the same displacement for this node as this element should? Yes. So there's a lot more stuff to do. Another thing that you will see is we have, I'm trying to figure out how much in depth I should get into this without scaring you guys, basically. And that is this. When you look at the element formulations, we have our stiffness matrix, K, is equal to the double integral of B transpose times C times B all over the element surface. What we actually do, and I'm trying to show you the things you'll encounter in Abacus, is one thing that we can do is specify something called reduced integration. Reduced integration. Basically, if I were to have an element, let's erase this. Let's say that I had a nice square element, and let's say that I had an axis going right through the center. And let's say that my element goes from -1 to 1 and -1 to 1. If I'm integrating from -1 to 1, do you guys remember in math that that's actually something very special? Yes, you can actually express it as a summation. It's called Gauss integration. So what you'll find out is that in Abacus, what we do, again, this, you don't have to write this down, but we take an element that's in a random spot in the beam. So let's say we take this element over here. Oops, I want to make it really weird because you can make elements whatever you want. Something like this. We take this element, oops. Let's see if I can make it bigger. No? Okay. We take this element, which goes from, I don't know, let's say 2 to 3, 5 to 6. And the first thing that we actually do is we make it into an element like this, where the axis is right through the center and it's nice and square. This will go from -1 to 1, -1 to 1, and that eliminates our integration. From here, we can find the stiffness, and then we can bring it back to its original position with the stiffness. Now, I know that this makes no sense at all, especially how I drew it, but basically, I just want to show you guys one thing, and that is this. When we take our element that's distorted and from random bounds and convert it into this particular way to avoid that integration, there's one source of error. And this is all I want to show you guys, the source of error. The more distorted your elements are, so is this a rectangle? No. The more distorted they are, the less accurate the actual results will be. You want to avoid distortion. It turns out that if I were to take an element that was, let's say like this, actually, I wanted a rectangle. If I were to take an element that is rectangular, and let's say that this goes from 0 to 6 and then 0 to 100, if I were to take an element that's perfectly rectangular, bring it into this system and bring it back, the results are actually going to be exact. So that's a key thing. You can have long elements, or you can have tall elements, you can have whatever. Just make sure that they're square or rectangular. Because what happens is when you convert here and then convert back, the results are going to be identical. If I have a distorted element and then bring it in and then bring it back, that's when the results get a little bit messed up. So the only thing I'm trying to show you guys is avoid this distortion. That's it. Another thing that I want to just touch upon really quick is this, this common thing, because one of the questions you may get asked when it comes to the finite element method is how did you solve it? how did we create our equations? How do we find the stiffness matrix? What approximation method? Virtual work. You guys have worked with virtual work. Basically, you take a scenario, you define an approximation, and you get a bunch of equations. How did you solve the equations? You used Mathematica. You just want solve. Another key thing in the actual finite element method is how do you solve those equations? Because another thing too is those equations, once you start talking about damage, plasticity, all that stuff, they're nonlinear. What we actually do is we use something called the Newton-Raphson method. So you guys probably heard about that before, where it basically finds the tangent line of a curve. I'm only showing you this because I found this really funny. So let's say that this was our curve. What the Newton-Raphson method does is it basically finds, oh, yellow would probably not show up very well. Let's go blue. It finds the tangent to the curve, like here. It comes back, and it basically does this procedure. And it's funny because when I was in South America studying earthquakes, the finite element prof there, he always went, then you solve it, and that's what it meant, the Newton-Raphson method. So it's one of those things, I'm not going to teach it to you, but what I'm trying to do is highlight all the aspects. If you look at the course, and if you're interested in this, I have all my lecture notes for all these things posted. I put all my lectures from 665 if you want to have a slower look at all this fun stuff. But what I want to do is just, again, give you the basics. And then I want to ask you, what questions do you have? Again, I tried to show you the basics, but I know that you probably have some questions of your own. No questions?